Hi, in this video I'm going to be talking about solar sails. It's a method of propulsion by the sun's radiation which doesn't need any fuel. Although solar sails are often thought as being new, something for the future, the actual idea has been around for quite some time. It was first proposed back in 1608 by the astronomer Johann Kepler and popularised in The Sunjammer, a 1964 short story by Arthur C. Clarke, which featured racing of space yachts powered by solar sails. In fact, there have already been 3 missions in which solar sails have played a prominent part. A little bit later in this video, I'll go into them in more detail. There are 2 types of solar sail. The first type is when light is reflected off a surface, and all solar sail spacecraft used this method of propulsion. A newer method is when light is diffracted or bent as it passes through a small opening. This is a new approach and it has certain challenges with it, and so far no diffractive solar scaled spacecraft have been built. So I'll just touch upon this. There's a little Science Direct article if you want more information about it, and here's the link. The underlying principle of solar sails is quite simple. Light consists of a stream of photons, and whenever a photon hits a reflecting surface, it's reflected back at the same angle it strikes it, shown by the Greek letter theta above. Some of the photon's momentum is transferred to the mirror, the reflecting surface, pushing it away in a direction at right angles to the surface. And the net effect of the vast number of photons in sunlight is to generate a force, a thrust, accelerating the mirror away from the sun in the direction shown by the red arrow. Now, because the direction of thrust is always at right angles to the reflecting surface, it's possible to change the direction of thrust simply by tilting the mirror. You can see this, how it would look at 15 degrees, 45 degrees, and 80 degrees. What the diagram also shows is the smaller angle of reflection, the greater the thrust. At 15 degrees, there's a lot more thrust than there is at an angle of 80 degrees. I've put an equation here for the thrust at 1 AU. 1 AU is the mean distance from the Earth to the Sun. As you can see, the thrust is quite small, 9 times 10 to the minus 6 newtons. A newton is the metric, the scientific unit of force, and there are 4.48 newtons in 1 pound force. And this table here shows the strong cosine square dependency. So at an angle of 60 degrees, you only get a quarter of the maximum thrust if the sail is head on. The other interesting thing is that the solar irradiance falls as the inverse square of the distance from the sun. So that means the thrust must also fall by the same relationship. Now that's for reflected light. Now some photons will be absorbed rather than reflected. And for absorbed photons, the relationship's a little bit different. Direction of thrust is always in the direction of the photons are travelling, and the dependency is only cosine of the angle rather than cosine squared. And the other thing, of course, is absorbed photons heat up the sail. Some other things to think about why you might not get this maximum thrust is the sail might be bowed or uneven. That means different parts of the sail, the thrust will actually be in slightly different directions, so there'll be a slight cancelling out of thrust. You won't get the maximum. Or the sail might have wrinkles in it. So, all in all, here are some numbers. The maximum thrust is given by this equation here. So if we put in some numbers for a 30 metre by 30 metre solar sail, it's got an area of about 900 square metres, well exactly 900 square metres. And if we then work out the acceleration that a spacecraft power this sail would achieve, it's actually very small. It's only 0.185 millimetres per second. But this is the beauty of solar sails. Over a period of one day, that's 86,400 seconds, the spacecraft can change its velocity by 58 kilometres an hour. And if we just left it for 6 months, then the spacecraft could change its velocity by over 10,500 kilometres an hour without any fuel being used. And that's the beauty. But in reality, things aren't quite as simple as that. The spacecraft will be in orbit around the sun, and the force of the sun's gravity will pull it towards the sun. So we need to take into account the spacecraft's initial orbital parameters, that's its distance and the velocity it's moving already when calculating its trajectory. If a solar sail spacecraft passes another object, such as a planet, then the effect of gravitational force due to the object needs to be taken into account. And the thrust provided by the solar sail and its gravitational force are constantly changing as the distance to the sun changes. And if the orientation of the solar sail sun changes, the magnitude and direction of the thrust will change. But even so, the small acceleration which mounts up over a period of time, producing large changes in velocity, could make them suitable for powering uncrewed spacecraft travelling between planets. And I'll talk a bit about this next. So let's see how solar sail spacecraft compare with traditional rockets. So take, for example, a mission called the ExoMars Trace Gas Orbiter, TGO. This was launched in 2016 to investigate the Martian atmosphere, particularly methane, and the presence of methane could be evidence of current biological processes on the planet. And it's been a success in the sense that no methane has been detected. And we also know a lot more about the water distribution on Mars because the orbiter also maps the distribution of water ice and hydrated minerals just below the surface. And this is crucial for understanding the planet's past and present climate and possibly looking for water for future human missions. Okay. If we look at the orbit it's in a circular orbit 400 kilometres above the planet's surface, inclined at 74 degrees. And this is quite steep inclination and enables us to see most of the planet's surface. Now, its trajectory was like this. It was launched in March 2016 on a Russian Proton launcher, which weighed 710 tonnes at liftoff. And the vast majority of that 710 tonnes was fuel. And after launch, it then fired its upper stage 4 separate times, and the upper stage had a power of nearly 20,000 newtons, and this set it on its way to Mars, where it arrived in October of that year. Now, when it arrived at Mars, it didn't actually start science operations for nearly 18 months later. And the reason for this is because of its orbit around Mars, which I'm going to show you now. When it arrived at Mars, it was in a highly elliptical orbit, only 300 kilometres above the planet at its closest and 9,600 kilometres as its furthest away. And it had to reduce its orbital speed and its orbit into a more circular orbit by using aerobraking. That's being slowed down through the upper regions of Mars's atmosphere. And this whole thing took 18 months, and it also had to fire its thrusters a number of times to circularise the orbit. And the reason for this is that there just wasn't the amount of fuel to do a straight insertion into the required orbit. And this is fairly standard. It took far longer to get it in the right orbit around Mars than it actually did to get it to Mars, which is actually quite interesting and illustrates the fact for these sort of interplanetary uncrewed spacecraft, fuel is a consideration. Fuel is a really big consideration. Okay, now let's see how it compares with a solar-sailed spacecraft. Think about a solar sail spacecraft in orbit 1 AU from the Sun. Well, the Sun's gravity pulls it towards the Sun with a strength of 0.15 newtons. That's given by this expression here. Now, if we assume that the material of the sail has a density of 5 grams per square metre, and it's a big sail, 1,000 square metres in area, that would give it a mass of 5 kilos. Let's assume the structure to support it also has a mass of 5 kilos, because you can't have a sail without anything to support it. And the spacecraft mass, let's say, is 15 kilos. The total mass of the spacecraft and sail is 25 kilos. This means that the maximum thrust is 0.0075 newtons. Now, what we see here is the maximum thrust is only 5% of the Sun's gravity. And the interesting thing is, as the Sun's gravity and also the intensity of sunlight both fall as the inverse square of the spacecraft's distance, no matter where the spacecraft is, then its maximum thrust will always be a 20th of its pull towards the Sun by the Sun's gravity, because both vary with 1 over r squared, where r is the distance from the Sun. So if we start off at a distance of 1 AU from the Sun, that means the sail is in a circular orbit 1 AU from the Sun, and keep it tilted at 30 degrees to the normal. So you can see here I've marked the strength of the Sun's gravity, and because the sail's thrust isn't bang on to the normal, its maximum thrust is slightly weaker than we've calculated. This is the trajectory that it's going to arrive at. So you can see after 2 years it arrives at 1.47 AU from the Sun. So you can get roughly to the distance of Mars after 2 years. Now let's angle the sail like this, so the thrust pushes against the direction in which it's travelling against the Sun. Then this is the trajectory we get. It's quite interesting. The sail then spirals inwards. After 2 years, it gets around about half a AU from the Sun. So that's between the distance of Venus and Mercury. And finally, let's look at the example where the sail is at the normal, so the photons hit it head on. In this case, you get the maximum possible thrust. And what happens then is the sail goes into an elliptical orbit around the Sun. So its period goes from 365 days to 406 days. The first solar sail spacecraft was Icarus, which was launched with the Japanese spacecraft Akatsuki to Venus back in May 2010. It had a large solar sail area, which enabled it to develop 1.1 millinewtons of thrust. Although it was launched with Akatsuki, its solar sails enabled it to drift away from the spacecraft, and it arrived in Venus 2 days later, flying past Venus at a range of just over 80,000 kilometres. Icarus is still in orbit around the Sun, but it's no longer in contact with Earth. It was able to test various things. Probably the most interesting one was by changing the reflection of different parts of the solar sail, which enabled it to be tilted at different angles and provided a bit of steering. The next solar sail spacecraft was LightSail 2. This was privately funded by the Planetary Society. There was actually a LightSail 1, but this didn't use solar sails for propulsion. It just checked that the sails would unfurl. LightSail 2 used its sails to manipulate the spacecraft to a higher Earth orbit. Interestingly, one of the things it had on board was a mini DVD containing the Planetary Society member roster. The final solar sail mission was NASA's Advanced Composite Solar Sail System, called ACS-3, launched in 2024. This had a solar sail with an area of 80 square metres, so that's intermediate in size between Icarus and LightSail 2. And one of the things they wanted to test was making the booms out of new material, which would be much lighter than existing metallic booms and would enable the whole spacecraft be packed up into a CubeSat, roughly the size of a microwave oven. And the idea is this technology, now it's been proven to be successful, could be used in future missions for much larger solar sails. So we can draw some conclusions about all the stuff we talked about so far. Solar sails provide a constant weak thrust all the time, works all the time. So you can't launch a spacecraft into Earth orbit from a solar sail powered spacecraft where you need a very high thrust to overcome the Earth's gravity. This technology will continue to develop and will get thinner and larger solar sails. So solar sails could be viable means of propulsion for moving small, light spacecraft up and down between different Earth orbits, and perhaps around the orbits around the terrestrial planets. Interestingly, NASA proposed a solar cruiser mission to the Earth-Sun L1 point, which would have launched in 2029 and would have incorporated solar sails. However, it didn't quite make it through to the final round of missions selected to be built. Interplanetary transfer missions between the 4 terrestrial planets. A solar sail-powered spacecraft, after it had travelled to Mars, could reverse the direction of its solar sails and return back to Earth or onwards onto Venus. Perhaps solar sail spacecraft could be used to explore nearby asteroids. Proxima Centauri b is an exoplanet discovered orbiting Proxima Centauri, the closest star to the solar system, in 2012. It lies at a distance of 4.2 light years away from Earth. Its mass is around about 1 Earth mass. Its radius, perhaps 1 Earth radius, and it's likely to be, with that mass and radius, a rocky terrestrial planet. Its temperature is Earth-like, is in the habitable zone around its planet, around its parent star. Whether or not it supports life is unknown. Proxima Centauri is a red dwarf, which means its brightness can flare up and down greatly, which might make conditions difficult for advanced life forms to exist. To get there with conventional rockets, it would take 100,000 years. Now, solar sails won't help to get you there any quicker, because as you get further from the sun's radiation gets weaker, falls as the inverse square, as you've seen. And to get to AU from the sun, it would take 10 years, using the example of the solar sail we saw earlier, 5% of the sun's gravity. And that only takes you 2/5 of the distance to Jupiter. But in 2016, Yuri Milner, the investor, did announce an extremely ambitious project to develop the technology which would enable us to get there at some point in the future. Here are a few headlines from the announcement. Milner's plan was you'd spend an initial 100 million over 5 years to determine whether it was feasible at all. There'd be a much bigger investment to build a low power prototype where we test it, and then you'd spend an enormous amount of money building a system to take us to the nearest star. And I'm going to talk about now how this might work. The spacecraft themselves will be extremely small, perhaps only weighing a few grams. These are called star chips, and there'll be a fully functional spacecraft on a single waver containing cameras, navigation gear, comms equipment and a power supply. And you need to have a small size to achieve the very high acceleration with minimal force. Each spacecraft will be attached to an ultra-lightweight meter-sized light sail. There's only a few hundred atoms thick, and this sail will be made from advanced materials to be highly reflective and to stand the intense acceleration. In order to achieve this acceleration, we'd have to have a ground-based laser array. There would be hundreds of lasers, perhaps a kilometre across, and it would focus a massive amount of laser energy, 100 gigawatts, onto the light sails for a few minutes. And this intense beam would accelerate each spacecraft to about 20% of the speed of light. Obviously, once the spacecraft has been launched, then it can't alter its trajectory once the acceleration ceases. And going at a fifth of the speed of light, the journey time to the Alpha Centauri system, which of course includes Proxima Centauri, is 22 light years. And because of the risk of failure of an individual spacecraft, then the idea is there'll be thousands of these sent on the way, and only a small percentage would reach their target, and many would be lost due to collisions, for example, with interstellar dust on the long journey. None of the technology to do this exists today, but the hope by the breakthrough initiatives was that over time the technology could be developed to do this. For example, here is how the images could be sent back by using the laser on a sail as an antenna. But this isn't without its challenges, and I think these objections listed here seem quite realistic and would be quite difficult to overcome. So I think it's going to be a long way, if at all, before we see anything like this happening. Since the original flurry of activity back in 2016, there's been very little information on the Breakthrough Starshot project.